All right, there are two cases for addition. The first one is where you are adding one point, let's say this point over here, point A, to another point, and those 2 points are not the same point. So those points get added in this system by drawing a line between the 2 points, finding the point where they intersect, and going to the opposite side of the curve. So a straight line between 2 points, and you switch to the other side of the curve. This point over here that I've got the cursor at right now, the mouse cursor, is the sum of those 2 points. Now, that's pretty easy, okay? I mean, it's a curve in 2 space, take the 2 points, add them together. There's no good way to do, I should point out there's no good way to do subtraction, because if I had this point, I don't know which of those 2 points. I could have another point right here that hits that point that comes over here. So you can go addition direction, but you can't go subtraction. And that's really important. That is what's called the trapdoor capability of this operation. Is addition is one way only. So that's one of the 2 cases for addition. Now the other one is, suppose that this point is the same location as the point we want to add to. And that's doubling a value. So both points are the same, and we can't calculate a line between the 2 of them because there's 0 distance, and our point slope form of the line gets all ugly. So what we do is we take the derivative of it to calculate the slope of that point. We draw a line at that slope and we find out where it intersects. Now, an important detail here is that these elliptic curves are not functions, because there is more than one solution down here for every value. So when we do it, what we want to do is we want to take the derivative on the left-hand side, dy dx, at the same time as we take the derivative on the right-hand side. When we get the results, then we have these 2 derivatives, then we do our factorization, and then we get the result. Otherwise, nothing works out. But there's a way to get the derivative and the slope. It's not a function, but you can still do this. So we draw a tangent line to the elliptic curve through the point. This always intersects the elliptic curve. Why that is will become totally apparent later on when we start talking about the modulo arithmetic. But you can just accept it that it always intersects. And no matter where it intersects, then we then go to the other side, reflect this across the axis to find the point, and that is the sum of the value. Now, this doubling and summing stuff allows us to easily calculate what the results of a multiplication are, but since there is no subtraction, there is no way to do a division. So how do we do this with bigger values when we want to do multiplication? Now, this multiplication thing is referred to as double and add, and there are some specialized versions of it. If you go find the wiki or a Wikipedia page on elliptic curves, it'll go through some other versions of this that make it so that you can't have side channel attacks. It makes it more complex. But this just confused the living daylights out of me for the longest time, because there was all these explanations of d equals d0 plus this. And yeah, okay, we've got some math and we've got an algorithm, but let me explain it to you the real simple way. If I want to multiply by 151 in this example, n equals 151, so we're going to do this multiply, then we represent it as this binary number. Everywhere where there is a 1 in that binary number for what we're multiplying by, we're going to double. And then we're just going to take the values and add them up at the end. So 151 is 2 to the 7th, that's that very first one, plus 2 to the 4th, which is right there, plus 2 squared, right on down to 2 to the 0th, that's the last one. So we know that we're going to do this, and any one of these algorithms that does a double and add, you've got all this shifting of bits, but basically, in the size of the number, you can do a certain number of doubles, and you can do a certain number of adds. And doubles are fast because we take the tangent of the line. Adds are fast because we just have 2 points and we're adding it together. So the end result is that when we want to multiply some value p by 151 in this system, we have this result that is really easy to calculate here. And all we have to do is take the constant we want to multiply by, let's say the generator or whatever that constant is, break it out into It's binary form. Zeros we ignore, ones we double. When we get done with this, we add up the result and poof, quick multiply. And I think that that's just one of the most clever things of all time. That is just really sweet that you can just look at it as binary and do this multiply. So multiplication is easy. Division is impossible. And that's the trapdoor. Once we have division as impossible, there's no way to go back and factor the results from this. Once you have a result, it's stuck in a result form. And that's what you're looking for whenever you're talking about encryption. Is, yeah, here is a result, and I can only go forward. If I have one point, and I know that I got to connect to another point, then one point can be the public result, and the other point can be the private result. And you can only go forward. And you don't have your key distribution problems. You have public key encryption.